Okay, we just had our last class. I still can't believe that the term has reached an end, and I want to thank you again for the unclear or muddy points that you submitted at the last lecture, and I certainly wanted to honor all of them, and I thought that I have some time right now, as this is after class, to do the address the muddy point on Lewis structures, and to bring in formal charge, electron group geometry, naming, drawing, and the hybridization states, because some of you mentioned all those together, and I think that that was wise because they are all related, and the expectation is on the exam that you will probably be able to do all of these things with one molecule. So I want to do about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 examples, okay? And each one is important. We're going to start straightforward though, and let's start with ammonia. Was our first one on the list. Remember, ammonia is NH3, ammonium is NH4+. And if we were going to draw the Lewis structure, I have 5 valence from nitrogen and a total of 8 electrons here, because 1 each from the hydrogens. And my Lewis structure, I arrange the atoms around in no particular order, but at least being able to connect them. So 2, 4, 6, and then I have an extra pair, and that is my Lewis structure. The VSEPR, if I wanted to do electron group geometry, I would have to take this and apply VSEPR theory to it. And so in that case, I'm counting the electron groups around the central atom, 1, 2, 3, 4. And because I have 4, I know that my electron group geometry is, and I'm not going to write these out, I'd rather actually, if you take notes, it'll just fill up the page, and sorry, but it'll just work better that way. So again, the electron group geometry is 1, 2, 3, 4 tetrahedral. And so I'm about to draw my tetrahedral, but I don't want to put all the lines in. I'm not using a pencil. I'm going to place my lone pair first, and I do that. And then I have 1, 2, 3. Now in the lab, you did something fancy, dashed lines going to the back and more of a spear coming out. That's great if you can do that. I'll gladly accept that on the exam. But I think that this also depicts, fair enough, a 3-dimensional. And now what is the molecular geometry? A trigonal pyramid, okay? Because imagine, I'm just going to do this in pencil. If I were to join up the base here, it would be a triangle, and then up to the nitrogen, 1, 2, 3. I see that it's all encased inside a trigonal pyramid. That is my molecular geometry. I want to be able to draw it. That, without the cage and pencil on top, will suffice. And then we want to know what is the hybridization state, but only of a central atom, never of the outliers. And the hybridization state of nitrogen is, or any central atom, is actually, you're ready to answer that question once you do the electron group geometry, not necessarily the molecular geometry. Because we ask the same question to deduce. And the question is, how many electron groups are around the central atom? 1, 2, 3, 4. So I need 4 hybrid orbitals to accommodate these. And therefore, I need an S. And how many p's? If I need 4 total, I need 3 p's. So each orbital, nitrogen now has an atomic orbital that's a hybrid of s's and p's, or s and 3 p's, that points, it's called an sp3, and it has 4 of them. One is pointing in this way, overlapping with the 1s of hydrogen. One is pointing this way, overlapping with the 1s of this hydrogen, and so on. And one is pointing this way. In fact, that's basically what we draw in this hood. It's housing the lone pair of electrons. So that's a good place to start, ammonium. And then we've done acetic acid in class, but I want to do the acetate, ion. And the acetate ion is from your list of polyatomic ions in Chapter 3. I'm just going to fold this over so we have a clean sheet of paper. And those polyatomic ions in Chapter 3 are, we'll do a few here in this tutorial, but they're good ones to practice with for Lewis structures. Okay, acetate. So the acetate ion is a CH3COO minus, and we know that. We should know that. That's how we write it. So, yeah, it's the partner base of acetic acid, right? If I put a hydrogen here, I would have acetic acid. So this is, I guess, a condensed structural formula, sort of. And I want to do a Lewis structure on it. So I have 6, 12 plus 4 is 16, and 3 is 19, and 4 is 23, which is an odd number, but I add one more for the charge, and that's 24. So I have 24 electrons, and I know that I have a CH3 is like this. We were sort of doing Lewis structures, not complete ones, when we were doing the complete structural formulas for these organic looking molecules. C, now it's OO. Let me just follow the rules of Lewis structure. So my atoms are arranged and I'm making single bonds only. Okay, don't make that double bond. And I have 24 electrons total. 2, 4, 6, 8, 10, 12. And then I go to the outside. 14, 16, 18, 20, 22, 24. And because it's an ion, I'm going to put it in square brackets and put my charge. I shouldn't have put a circle around it because I do that for formal charges, but that is a possible Lewis structure for the acetate ion. Actually, it isn't complete yet because this carbon has 2, 4, 6 electrons and it needs 8. So the thing is, I can take a pair from here and make a double bond, or I could take a pair from here and put a double bond there. So in fact, this is not even one Lewis structure for the acetate ion. Rather, acetate ion has 2 what's called, I will write this one out, resonance structures. And they are the following. CH3 C double bond O, and this is still a Lewis structure, so there's really no structural bond angle implied. This is a Lewis structure. It's not VSEPR, but out of habit, I'm drawing it this way. And it would be like this. So that's one Lewis structure where I took that pair and shared it here. And so I have 2, 4, 6, 8 around the oxygen and 2, 4, 6, 8 around this carbon and 2, 4, 6, 8 around this. So that's a negative. Then I use my resonance arrows, a double-headed arrow. And the other possible resonance structure, of course, would be that this is a single bond and this is a double bond here. And those are the 2 resonance structures. And so there are 2 possible Lewis structures. So if the question says draw possible Lewis structures include any resonance, this is it. Okay, there are 2. This is not a proper Lewis structure. So that's my acetate ion. And I'm just going to add formal charges for practice here. And I'll put those in red. And formal charge 4 minus 1, 2, 3, 4 minus no lone pair electrons. So carbon is 0. Each of the hydrogens is 0. Carbon with 4 bonds is 0. Oxygen 6 valence minus 1, 2, 3, 4, 5, 6, 7. And so it's a minus 1. And this oxygen is, it better be 0 because all of my formal charges have to add up to the actual charge on the species. 6 valence minus all of the non-bonding, the lone, 1, 2, 3, 4, and half of the bonding, so 1, 2, and 6 minus 6 is 0. Same thing over here. I don't have to write them twice. It's the same molecule. Okay, so a single bonded oxygen is a formal charge of -1, and the double bonded oxygen in this case has the formal charge of 0. How about the, I won't ask you the overall molecular geometry of this molecule because there's 2 centers, but I can ask you, and will, on the, excuse me, the electron group geometry around this carbon, and that would be tetrahedral. I can ask you for the hybridization state of this carbon, and because there's 4 needed, it is sp3. And what is the molecular geometry around this carbon? And it is tetrahedral. This carbon, bring it over here. Let's make sure I'm still in view. Yeah. So this carbon has 1, 2. Now, do I do 1, 2, 3, 4? Am I counting 4? Nope. The number of electron groups, it's called an effective number of groups, and I always count the multiple bond as 1 because it's based on repulsion, remember? So I have 1, 2, 3. And in terms of the hybrid orbitals, I need a hybrid orbital for here, and for only one part of the, in fact, half of the double bond, because hybrids are used for sigma, and sigma bonds are single, but they're also just that direct overlap part of a double. Okay, so this carbon has an electron group geometry that is trigonal planar. It also has a molecular geometry that's trigonal planar, and we know that those two are the same when there are no lone pairs. The hybridization state of this carbon is sp2, 1 part s and 2 parts p, which as a linear combination would give me 3, and I need 3. So there you go. And I don't determine geometries or hybridization states of these outer atoms. They're not sort of in a central region. They are not the middle of a bond angle. That's how you know if something is central or not. So that's it for acetate. We have time for one more before someone knocks on my door. That was the acetate. Let's do the, not in red, carbonate ion, CO3 2 minus. Oops, sorry. The carbonate ion, CO3 2 minus. Okay, 4 electrons from carbon. 3 6 is 18, and 4 is 22, and 2 more is 24, so I have 24 electrons. The Lewis structure puts carbon in the middle, and I've got 3 oxygens. Make my single bonds, 2, 4, 6, lots of electrons left over. Go to the outside, 8, 10, 12, 14, 16, 18, 20, 22, 24. And so, and don't forget a -2. But this is not a good Lewis structure because I only have, I'm short on the octet for carbon. I need 2 more electrons there. So I note that, I think you're going to see this right away. I can take it from there, or I could take it from there, or I could take it from here. How do I choose? We don't. We say that there are 3 resonance structures for the carbonate ion, and they are 3 in which the double bond is sort of rotated in position here. And we can draw these. So I'll put it here this time, and you can verify that you are still just using 24 electrons, and square bracket it each time. Use your resonance arrows each time. Square bracket because it's an ion, and now I have zip, 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 and 6, and this, and -2. And there we go. I have 3 resonance structures, and now which one do you actually use as the basis for VSEPR? Well, before I tell you the answer to that, I wanted to let you arrive there yourself. What's the basis of VSEPR? It's repulsion. It's counting the effective electron groups around the central atom. And so here it would be 3, and here it would be 3, and we've quickly noticed that it's irrelevant which one I pick because it's not relevant. It doesn't matter where that one double bond is. Now if I had, no, it just doesn't matter at all. It's 3. So I can use any one of these to move forward. So I'm just going to pick the first one and say, all right, I've got 1, 2, 3 electron groups. And when that is the case, there's my central atom, I put them in a geometry that is trigonal planar, and I'll make this therefore a double bond, and I'll keep this signal, and I'll keep this, not signal, single, and then add, I don't know why I did it in red, I hope you can still see that okay, and like so, and each angle is 120. This one, and this one. They're all 120. Because I'm still dealing with an ion, I will do a -2. So if I want to do trigonal, if I want to do VSEPR, it's not necessary that you do a geometry for each of the resonance structures. Okay, if I ask you to draw the lowest structure, you have to show me there's resonance and do all 3. If I say draw all possible lowest structures, then I'm really pointing out to you that there's probably more than one. And in this case, if I'm asking for geometry, you can illustrate it using any one of the resonance structures. Most people like to look at it symmetrically, and most of you would probably put the double bond up there, but it doesn't matter. So the electron group geometry around this central atom is trigonal planar, and the molecular geometry is also trigonal planar because I have no lone pairs. To draw it looks like this. I'm just going through the list of the muddy points here. And hybridization state of this carbon again. 1, 2, 3 effective electron groups that I need to accommodate. I only ever accommodate one of a multiple bond because there's only one sigma in a multiple and a single is a sigma. So I have 3. I need 3 atomic orbitals that are hybrids. And therefore, I say that this carbon is sp2. So that bell is the person that I was expecting. And we are done, except for the formal charge. Formal charges, you can do them. That would be -1, -1, 0, and 0. Okay, we'll do the next in a bit.